Just as Nicholas Copernicus introduced the heliocentric model, another stunning revision of our understanding of the cosmos could emerge, sparking a debate known as the crisis of cosmology. This crisis is marked by significant discrepancies in our measurements and understanding of the universe's fundamental properties, such as its age, size, and rate of expansion. Neil deGrasse Tyson has noted that the discovery of the James Webb Space Telescope, JWST, has put an end to this debate with an image that defies physics. So, what exactly is this crisis, and how does the James Webb Space Telescope contribute to it? Well, contributing to it is a bit of an exaggeration. It's more like a review that has been underway. The crisis refers to a point at which our understanding of the universe is challenged, particularly in terms of its age and size, which are linked by a considerable margin of error. The introduction of the James Webb Space Telescope has been crucial in this context. Before this breakthrough, we were limited in how far we could see into the early universe, but with the JWST's improved capabilities, astronomers can explore much more distant galaxies, giving us new perspectives on the universe and challenging some of our previous conceptions. This advancement allows us to peer further back in time, closer to the Big Bang, and observe galaxies as they were forming, which provides critical data that can either support or challenge our existing models of the universe. To understand the crisis in detail, it is important to review the standard model of cosmology, known as the hot inflationary Big Bang model or lambda cold dark matter lambda CDM model. This model has been very successful in explaining various features of the universe, from gravitational lensing to the structure of the cosmic web and the growth of galaxies. The lambda CDM model posits that the universe started with a Big Bang, followed by a period of rapid inflation, and has been expanding ever since. It includes components such as dark matter, which exerts gravitational forces, and dark energy, which drives the accelerated expansion of the universe. However, each new observation, especially with instruments as advanced as the JWST, raises the possibility that our current model may be incomplete or need to be revised. The lambda CDM model makes specific predictions about the characteristics and behavior of galaxies at different stages of the universe's history. For instance, it predicts that galaxies in the distant past should be smaller, less developed, and composed of fewer heavy elements compared to those we observe in the local universe. This is because heavier elements are formed in the cores of stars and distributed through processes like supernova explosions, which take time to occur. According to this model, as we look further back in time, galaxies should be smaller, bluer, less developed, and less rich in heavy elements. This would lead us to expect to enter eras of the universe devoid of visible stars or galaxies. However, scientists have found contradictory evidence that challenges these predictions, resulting in a crisis in cosmology. The crisis in cosmology centers on the uncertainty about the age of the universe. Different measurement methods provide different results, leading cosmologists to struggle to reconcile these discrepancies. To try to address this problem, scientists use several methods to measure the age of the universe. One of them is the study of cosmic background radiation, which involves unraveling the history of the expansion of the universe and using mathematical models such as the Friedmann equations, based on Einstein's theory of general relativity, to determine the expansion rate and therefore the age of the universe at different times. The cosmic microwave background, CMB, a residual radiation from the early days of the universe, is a crucial tool for this measurement. Detailed maps of the CMB, such as those provided by the European Space Agency's Planck mission, offer valuable information about the composition of the universe. However, these maps lack data on dark energy, a major component of today's universe. Despite this limitation, scientists can use Friedmann's equations along with other observations to estimate the expansion rate of the universe at different times and ultimately determine its age. The Friedmann equations describe how the universe expands, accounting for the density of different components like dark matter, dark energy, and ordinary matter. By analyzing the CMB, scientists can infer the conditions of the early universe and extrapolate the expansion history up to the present day. Another approach to determining the age of the universe involves observing exploding stars, specifically type Ia supernovae. These supernovae act as standard candles because they have a known intrinsic brightness. By comparing their known brightness to their observed brightness, astronomers can determine their distance and consequently the expansion rate of the universe at different times. This method, used in the 1990s, played a crucial role in the discovery of dark energy, which is now central to cosmological measurements. It is especially useful for determining the Hubble constant, which is a measure of the expansion rate of the universe. Although not exactly constant, the Hubble constant is instrumental in charting the expansion of the universe since the Big Bang approximately 13.8 billion years ago. It has been observed that the cosmos has been growing steadily. NASA has noted that the implications of this rate are significant. If the expansion is slowing down, it suggests the presence of an unknown force, possibly dark matter, influencing this process. On the other hand, if the expansion rate is accelerating, it could indicate the presence and influence of dark energy, accelerating the growth of the universe. In January 2018, scientists found something interesting. Although several telescopes indicated that the expansion rate of the universe varied depending on the point of observation, the Hubble Space Telescope measured a faster expansion in the nearby universe, while the Planck telescope measured a slightly lower expansion in the more distant regions of the universe. This discrepancy in measurement highlights the vast scale of the universe and reminds us of the pioneering work of Edwin Hubble, who first proposed the expansion rate of the universe in 1929. Hubble's observations of distant galaxies revealed that they are moving away from us, indicating that the universe is expanding. This discovery was one of the cornerstones of modern cosmology. Now, considering the expansion of the universe independently of your cosmic location, you would witness the same phenomenon at the same speed at the Hubble expansion rate. Initial calculations were based on limited data, but with technological advances such as the Hubble and Gaia telescopes, we have been able to observe more variables and refine our measurements. Other telescopes use readings of the CMB to calculate the constant, although this method has its limitations due to the availability of supernovae for distant observations, which restricts our view of the universe. Since the discovery of dark energy in the 20th century, scientists have been impeded by the discrepancies between these two approaches to the age of the universe and its expansion rate. As measurement technology becomes more precise, smaller variations arise, driven by the development of more advanced systems. This progress ironically raises more questions rather than providing definitive answers. Although the differences are marginal, with only 10 to 20 million years separating the estimates given that the universe is approximately 13.77 billion years old, it still merits careful investigation. One possible explanation for this discrepancy is the possibility of flaws in our measurements of the CMB. Despite being one of the most precise measurements, it has been extensively tested since its launch in 2013 for validating its accuracy. Another perspective suggests a possible gap in our understanding of dark matter, raising the idea that it may vary over time and be related to dark energy or some other unknown factor. This possibility has led to numerous exploratory studies. The accuracy of supernova measurements is also questioned, as the complexity of star explosions can introduce uncertainty into the models we use. Resolving this uncertainty in supernova models could help resolve the discrepancy in measurements. This crisis in cosmology has been further aggravated by the discovery of the James Webb Space Telescope. According to Neil deGrasse Tyson, the JWST found objects in the universe that challenge our current understanding. This means that our scientific understanding needs a complete overhaul, but the problem is that we have no idea where to start. To understand the magnitude of this scientific apocalypse, let's look at the beginnings of the universe. About 150 million years after the Big Bang, stars, black holes, and star clusters began to emerge, possibly even as early as 50 to 100 million years later. However, these events should be relatively rare. What we don't know is how common galaxies evolved at later times, spanning events between 200 and 400 million years after the Big Bang. Recent JWST images reveal galaxies much more distant and therefore older than the standard cosmological model predicts. This discrepancy suggests that our model needs a significant update. The revelation that the expanding universe depended on galaxies is a fundamental innovation. JWST images show galaxies that formed much earlier than predicted by current cosmological models, triggering a crisis in the field. This problem is related to galaxies and redshift, which is a common measurement in cosmology. According to the Standard Model, hydrogen began to appear 400,000 years after the Big Bang when protons and electrons combined, leading to hydrogen recombination. This transformed the universe into a soup of hydrogen atoms with some helium and residual background. The gravity of the radiation then acted on small perturbations in this hydrogen gas, slowly collapsing them to give rise to the first stars. These early stars, composed primarily of helium and hydrogen, participated in nuclear fusion, creating heavier elements such as carbon and nitrogen. These elements played a critical role in galaxy formation by absorbing, heating, and emitting cooling photons, which facilitated the coalescence of gas into galaxies. The process of galaxy formation and evolution is complex and involves many stages, including the merging of smaller structures to form larger ones and the ongoing formation of new stars from interstellar gas. However, the JWST has observed galaxies that formed much earlier than predicted by our current models, suggesting that we may need to revise our understanding of the early universe. This new data challenges our existing theories and raises questions about the processes that led to the formation of the first galaxies. The implications of these discoveries are profound, as they could lead to a significant shift in our understanding of the universe and its origins. To further elaborate on the crisis in cosmology and the transformative impact of the James Webb Space Telescope, JWST, it is essential to explore additional aspects of our current understanding and how new observations challenge this knowledge. One crucial area of ongoing research is the nature of dark matter and dark energy. While the lambda-cold dark matter, lambda CDM, model incorporates dark matter as a vital component that influences the formation of large-scale structures in the universe, the exact nature of dark matter remains elusive. It is theorized to consist of particles that do not interact with electromagnetic forces, making them invisible and detectable only through their gravitational effects. Various candidate particles have been proposed, including weakly interacting massive particles, WIMPs, and axions, but none have been definitively identified yet. Similarly, dark energy, which is responsible for the accelerated expansion of the universe, remains a profound mystery. It is often described as a property of space itself, or as a form of energy that permeates all of space and increases the rate of expansion. The exact nature of dark energy could fundamentally alter our understanding of the universe's fate. If dark energy is a constant, the universe might continue to accelerate indefinitely. Alternatively, if dark energy varies over time, it could lead to a dynamic and complex future for cosmic expansion. The JWST's ability to peer deeper into the universe than ever before could provide critical insights into these enigmatic components. By observing the formation of the earliest galaxies and stars, the JWST may offer clues about the conditions that led to the emergence of dark matter and dark energy. For instance, studying the distribution of dark matter in the earliest galaxies could help pinpoint the nature of dark matter particles. Observations of the rate of cosmic expansion in these early epochs might shed light on the behavior of dark energy in the universe's infancy. Another intriguing aspect influenced by JWST's discoveries is the study of cosmic reionization. This epoch, which occurred approximately 400 million to 1 billion years after the Big Bang, marks a period when the universe transitioned from being opaque to transparent. During this time, the first stars and galaxies emitted intense ultraviolet light that ionized the surrounding hydrogen gas. Understanding reionization is crucial for comprehending the formation and evolution of the first galaxies, and it could provide information about the early conditions of the universe. JWST's observations of high-redshift galaxies, galaxies that are so distant that their light has taken billions of years to reach us, offer a unique window into this early reionization era. These observations could reveal how the first galaxies contributed to the ionization of the intergalactic medium and how their radiation affected the surrounding environment. If JWST detects more complex and evolved galaxies at earlier times than predicted, it may indicate that the process of galaxy formation and reionization was more rapid and complex than previously understood. Additionally, the JWST's capabilities extend beyond the early universe and into the study of exoplanets and their atmospheres. By analyzing the atmospheres of distant exoplanets, JWST can search for signs of habitability or even biosignatures. This includes the detection of atmospheric composition, such as the presence of water vapor, carbon dioxide, and oxygen, which are critical for understanding the potential for life. The detection of such elements in exoplanetary atmospheres could provide clues about the conditions necessary for life, and inform our search for habitable worlds beyond our solar system. Furthermore, the study of galaxy formation and evolution in the context of JWST's observations challenges our assumptions about the hierarchical growth of galaxies. Traditional models suggest that galaxies grow by merging with other galaxies and accreting gas over time. However, if JWST's data show that massive galaxies formed much earlier than expected, it may imply that there were different mechanisms at play or that our models of galactic evolution are incomplete. This could lead to a reevaluation of how galaxies assemble and evolve over cosmic timescales. Another dimension of the crisis in cosmology is the need to reconcile observations across different wavelengths. The JWST, with its advanced infrared capabilities, provides data that complement observations from other telescopes such as the Hubble Space Telescope, which operates primarily in the optical and ultraviolet wavelengths. Integrating data from these diverse sources is essential for constructing a coherent picture of cosmic history. Discrepancies between different observational techniques could reveal new physics or highlight gaps in our current models. The interplay between observational data and theoretical models is a dynamic aspect of scientific progress. As new data from JWST and other observatories are integrated into our understanding of cosmology, theoretical models must be adjusted to account for new discoveries. This iterative process is a fundamental characteristic of scientific inquiry and demonstrates how theories evolve in response to empirical evidence. In conclusion, the crisis in cosmology, intensified by the groundbreaking observations of the James Webb Space Telescope, underscores the evolving nature of our understanding of the universe. The challenge lies not only in interpreting new data but also in integrating it into existing frameworks or developing new models that better explain observed phenomena. As our observational tools and theoretical approaches advance, we move closer to unraveling the profound mysteries of dark matter, dark energy, galaxy formation, and the early universe. This ongoing exploration exemplifies the dynamic and self-correcting nature of science, where each new discovery leads to further questions and deeper insights into the cosmos.